Hello, my name is Andrei Kulikov, and I would like to talk about some convolutional method using on time series. While studying some Kaggle courses, met that uh, convolution can be used on a time series that is one dimension array. So let's watch the details. So I have a data set uh, time series with mean temp and some other features. I'll work with mean temp feature. So some Kaggle code. So I load this data set, make some plots of it, then the plots of all of the features. Strange. Okay, here is the data. Then I take only a mean temp column and continue work with it. So what about beautiful? What about convolution? So it's you this method use kernels. So what is kernels? We can represent kernels as small arrays. Kernels define how a convolutional layer is connected to the layer that follows. The activations in the network we call feature maps. They are all they are what results when they show what the results the result when we apply a filter to an image. They contain the visual feature the kernel extracts. Yes. So images are two-dimensional, and so our kernels were 2D arrays. A time series is one-dimensional. So what should the kernel be? Yes, 1D array. Here are some kernels sometimes used for on-time series data. So it is a simple array of these characters. Okay, later. So the convolution and pooling operations share a common feature. They are both performed over a sliding window. With convolution, this window is given by the dimensions of the kernel, the parameter kernel size. With pooling, it is the pooling window given by pool size. Uh-huh. So convolution on a sequence works just like convolution on an image. The difference is just that a sliding window on a sequence only has one direction to travel, left to right, instead of the two directions on an image. And just like before, the features picked out depend on the pattern or numbers in the kernel. So here is the code, so I can use some of the uh, kernels here. Then I reformat my data to TensorFlow and start here the transformation of the data. So I use here two parameters like stride and like padding. So what is stride? Stride. The distance the window moves at each step is called the stride. We need to specify the stride in both dimensions of the image, or in my case, in series. One for moving left to right and one for moving top to bottom. This animation shows strides 2 and 2, a movement of 2 pixels each step. What effect does this stride have? Whenever the stride in either direction is greater than 1, the sliding window will skip over some of the pixels in the input at each step. Yes, yes. You see, it skips this and boom. Okay, because we want high quality features to use for classification, convolution layers will most often have strides one and one. Increasing the stride means that we miss out on potentially valuable information in our summary. Okay, and what is padding? When performing this sliding window computation, there is a question as to what to do at the boundaries of the input. Staying entirely inside the input image means the window will never sit squarely over those boundaries pixels like it does for every other pixel in the input. So what the convolution does with these boundary values is determining by its padding parameter. In TensorFlow, you have two choices, same or valid. When we set valid, the convolution window will stay entirely inside the input. The drawback is that the output shrinks, loses pixels, and shrinks more for larger kernels. And the same padding is to pad the input with zeros around its borders, using just enough of them to make the size of the output as the same as the size of the input. Okay, it is about convolution method, but what about series? So the first type of the kernel is called detrend. So here is the result, and the length is one less than the input. Okay. As for the average, here is the result. It does not graphically differs strongly from the input, but it has less data. And as for this, it's called here Spencer. It has less data. So, in fact, the detrend kernel filters for changes in the series, while average and Spencer are both smoothers that filter for low frequency components in the series. Changes and okay. If you are interested in predicting the future popularity of each terms, you might train a convent on time series like this one. It will try to learn what features in those series are most informative for the prediction. Though convents are not often the best choice on their own for these kinds of problems, they are often incorporated into other models for their feature extraction capabilities. So as for this material, I'll remember and once make some experiment with using CNN on data on a time series modeling, but I'll do it later. I was a little bit shocked when I saw this information. Because of that, I shared it with you. So thank you very much. Thank you, Kegel. You are great. Bye bye. See you later.